If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Please share it with all others who might benefit. Let's get started.
So we are talking about the activation functions, and in this tutorial, we're going to talk about what makes an activation function a good activation function. See, understanding the activation functions is really important for the overall understanding of the neural networks because these play a very crucial role. In this video, what we have in mind is that we'll talk about the key characteristics of a good activation function, and then we will try to look at all the popular activation functions through that lens. So we'll be able to easily interpret the strengths and weaknesses of different activation functions. So let's look at these critical properties of the activation function one by one. So these properties can be divided into two categories: desirables and non-desirables. Let's look at the first property. The first property is a desirable property, which is non-linearity. Second property is differentiability, and this is again a desirable property. And don't worry, we'll explain each of these one by one to you once we finish listing them down here. The third important property is the zero-centeredness. This is again a desirable property. Next is computational efficiency, very much desirable. And the last one on our list is the saturation effect, which is a non-desirable property, which means if an activation function has this property, it is actually bad for the activation function. Let's glass through each of these one by one. So when it comes to non-linearity, what do we mean by that? In fact, we did an entire tutorial prior to this just to explain why the activation function should be nonlinear. But just to summarize, when you have linear activation functions, you can reduce an entire network to a single neuron. So what's the point of having a network when a single neuron is just about as efficient? Nonlinearity is very much desired because this makes us capable of making complex decisions. If we have a linear activation function, the linear activation functions of the linear activation functions again tend to be linear, and they don't really help us achieve much when solving complex problems. Next is differentiability. Now, this is a very, very important property, and let's understand it a little closely. Let's look at a neural network, which is receiving these inputs, x1 and x2. Then at the hidden stage, we do an aggregation. We are representing it by z. Then some activation is applied. Let's say we are representing it by f, is some function. Then again, we connect these hidden neurons to the output neuron. Again, an aggregation happens and an activation happens. Finally, we generate an output, which is called y hat. So when we are solving real-world problems, we will always be given an actual y value. But given the inputs, we will be predicting a y hat value. So now for the time being, let's just try to concentrate on this part. You can imagine after the activation function here at the hidden neurons, you will be generating some output. By the way, these z and f values are just representative. Don't consider them to be the same everywhere. These are just the representation. So we may use a different activation function for the hidden layer and a different activation function for the output layer. That's very much permissible. Likewise, the value of z that you see here is not the same as the value of z here. It is just representing an aggregation. But after the activation at the hidden layer, you can imagine some outputs will be generated. And let's say these are represented by h11, h12, and h13. Generally, the way we name these is based on the arrow head and the arrow tail. So it is h11. Why? Because there's only one neuron in the output layer and it's connected to the first neuron of the previous layer. Why this is h12? Because the connection is between the first neuron or the only neuron of the output layer and the second neuron of the previous layer. Likewise, the only neuron of the output layer, that's 1, and the third neuron of the hidden layer, that's why we have named it. These are the outputs from the activations at the previous layer. Now, you'll also have the weights associated with each of these connections, and you're simply going to aggregate these. So you'll write something like W11 H11 plus W12 H12 plus W13 H13. That's the aggregation Z. That again goes through some activation, and that gives an output. Now, when we get this output, we want to essentially compare it with the actual or the ground truth value. How far we are in our prediction compared to the actual label. So for this, we'll define a loss function. Let's say this is a loss function, which is simply a squared error loss function. And we will be adding it up for all the records. But as of now, let's just say for one record, we are talking about the difference between y, which is the actual value, minus the y hat, which is the predicted value, squared. Now, since we are talking about differentiability, So we will have to understand how this L changes with respect to the changes in y hat. So for this, we can see the expression like this. Dou L by dou y hat. It's a partial derivative. How is loss affected by a change in y hat? But can we further trace it back? How is y hat affected by the aggregation that happened at the previous layer? So we may write it like this. So loss depends on y hat depends on the aggregation that happened at the previous stage. And the previous stage aggregation would eventually depend on these weights. So we are generally representing it by dou W. So it's a chain rule that we are seeing here. Loss depends on y hat depends on z depends on w. Now, if you see, all these are derivatives. All these would require these functions to be differentiable. And that's why the activation function being differentiable is very, very important. We'll be talking about this separately in a video on backpropagation. But for the time being, just understand this, that it is important for an activation function to be differentiable. Because the whole idea behind the neural networks is to be able to improve the loss or reduce the loss by changing the weights. You can imagine this dou y hat and dou y hat will get cancelled. Dou z and dou z will get cancelled. It's just a representation. Eventually, we'll be talking about how is the loss affected by the change in weights. And so would be the case with biases, which we have not shown here just to keep it simple. But eventually, we'd also want to see how the loss is affected with respect to the changes in the weights and biases. So differentiability becomes very, very important, and this is a desired property of an activation function. Next is zero-centeredness. Now, this is important to understand. Let's say we take a function, and we are talking about a function which is like this. How is this zero-centered? Are we talking about x-axis? No. When we talk about the zero-centeredness, we are essentially talking about zero-centered at y. So if you see this function attains a value 0, half of it is above 0, for y-axis and half of it is below 0 for y-axis. Such functions are called zero-centered functions. Now, what is the advantage of a zero-centered function? So a zero-centered activation function basically improves the learning efficiency by ensuring balanced gradients. Gradient is basically a vector representation of the derivatives, you can say. And we saw differentiability in derivatives are very important for activation functions. So it ensures balanced gradients and it leads to faster convergence. So if you just want to take away 1 point from zero-centeredness, you can imagine this will be faster convergence. What do we mean by convergence? It achieves its objectives faster. If your objective is to minimize the loss when you're training a neural network, you'll be able to achieve that faster when you have a zero-centered function. That's the reason we prefer such functions. Next is computational efficiency. Now, this is again a very simple point. Let's say we have two functions. First is the max of 0 or x, and second is 1 over 1 plus e raised to the power negative x. Which one is easier to compute? Let's say the value of x is 1. This function would be max of 0 and 1. You'll straight away give the answer is 1. And what would this function be? 1 over 1 plus e raised to the power negative 1, which is 1 over e, and e is 2.718. I hope you get the point. This will be more complex calculation compared to just finding the max. So if our activation function is easy to compute, it will be called computationally efficient. And this is another property that we might want to keep in mind when choosing the activation function. The last one on our list is the saturation effect. What is the saturation effect? Let's once again take a graph. And what do we mean by saturation? So if you see these ends here are flat, what happens when you try to see a derivative of this activation function with respect to, let's say, x in this case? It will be 0. The line is flat. The line is not changing. As we keep on changing the values of x in this region, there is no change in the activation function. Similarly, at this end, if you keep on changing the value of x, there is no change in the activation function. So this is called saturation effect. If we reach a stage where the derivative of the activation function becomes 0, it is called a vanishing gradient problem. Essentially, the network would stop learning after that. Why? Because it has hit a value 0 and it's not able to recover from that. Once you enter here in the range of 0, you would remain 0 forever. So is the case here. So once again, what is the effect of saturation? The saturation effects are bad in activation functions because they cause gradients to vanish. They become minimal or 0. This slows down the learning and can prevent the network from converging effectively, especially when we're talking about deep neural network. Now, the example I gave you when explaining differentiability showed just one part of the network and we looked at the chain. Imagine if it is a deep network, we would have gone back to previous layers, all previous layers. And if you have a vanishing gradient problem, you'd hardly be improving anything there. That's the point. So with this in mind, we have an intuitive understanding of the critical properties of the activation functions. Now, I'm not saying that this is an exhaustive list. We can have more properties. For example, we may talk about the continuity of the activation function or the monotonic properties of the activation function. There could be many more, but these are the ones that you definitely need to know. With this template in place, now what we intend to do in the next video is this. We will list out all the popular activation functions and try to put a tick or a cross with respect to these properties so that we have a fair idea about the strengths and weaknesses of the popular activation functions. We'll start with the step function. We'll move on to the sigmoid, tanh, ReLU, leaky ReLU, LU, and swish. These are some of the popular activation functions. Some of them are relatively more advanced, but a must-know at this stage. So next, we start with each activation function one by one.